Welcome to The Explainer. Today, we're exploring the invisible infrastructure that makes streaming video globally possible. Have you ever actually wondered what happens behind the scenes when you hit play on a video? Well, we're going to uncover the massive, hidden architecture that brings multimedia right to your screen.
Okay, let's dive right into this. 10%. That is just a staggering statistic. According to our sources, YouTube alone accounts for up to 10% of all internet traffic. Just think about the sheer volume of data moving across the globe every single second just to deliver those videos. It's wild. And so, this brings us to a really fascinating question. How exactly does the internet handle this massive load without just breaking? Today, we're taking a journey from the life of a single, tiny video packet all the way up to the massive global infrastructure that keeps the internet from collapsing under the weight of our binge watching.
Let's start down at the micro level with Section 1, the unseen protocols. You see, standard internet protocols like TCP or basic UDP, they just aren't enough for real-time video. Real-time traffic is a completely different beast from regular web traffic because it actually has to be played out at a predetermined rate to be, well, useful. To make this work, we need a special alphabet soup of protocols. First up, we've got RTP, the Real-Time Transport Protocol. Its main job is to literally carry the voice and video traffic back and forth across the network. Then there's its little sister protocol, RTCP. Now, it doesn't transport any media samples itself. Instead, it provides crucial feedback on network properties, keeping a constant eye on things like delay and jitter, and it makes sure your audio and video streams stay perfectly synced up. And finally, we have RTSP, which operates exactly like a VCR remote control for your streaming media. Just think about these text-based commands: describe, set up, play, record, pause, tear down. It's literally a remote control. Now, what's really fascinating here is a clever trick engineers use. While RTSP and RTP have their own designated ports, a lot of corporate firewalls automatically block them. So to get around this, these text-based RTSP commands are often disguised as regular HTTP web traffic running over TCP Port 80. By pretending to be standard web traffic, they sneak right through those firewalls, making sure you can watch your stream without the network administrator getting in the way. Pretty sneaky, right?
Moving on to Section 2, surviving the journey, jitter, and loss.
So when you're streaming stored media like a movie, the absolute delay of the network matters less. It really just affects how long it takes for the movie to start playing. What actually matters is the variation in that delay, which brings us to a crucial definition: jitter. Even a tiny amount of packet jitter can completely ruin a streaming experience, causing jerky video frames or making the audio sound completely unintelligible if the media is just played out exactly as it arrives. To fix this, media players use buffering. They gather up the incoming packets, smooth out the timing delays within an internal buffer, and only play the media once the timing is perfectly regulated.
But wait, how do we deal with packets that don't just get delayed, but get completely lost in the ether? Enter forward error correction. It's like magic. The media server mathematically combines standard packets A, B, C, and D to construct a single parity packet, labeled P, and then sends all 5. So if packet B gets lost in transit, no problem. The media player can take A, C, D, and that parity packet P and construct the missing packet B right on the fly. The stream never stops, and you, the viewer, never notice a thing.
There's another brilliant trick to survive network loss, and it's called the interleaving strategy. Instead of sending samples in perfect chronological order, the server mixes up the media samples before transmission. It transmits packets filled with non-sequential samples. Then, when the receiver gets them, it unmixes them back into the right order. Why go through all this trouble? Well, because if a single packet is lost in transit, you don't lose a massive half-second chunk of audio all at once. Instead, the loss is spread out into tiny little fractions of a second across the stream. Your media player just interpolates those tiny gaps, making the loss practically invisible to your eye and ear. It's a really elegant solution.
Section 3, the scaling problem. Okay, so we figured out how to safely get a video stream to one person. But what happens when the entire world wants to watch the exact same video at the exact same moment? That massive spike in demand is known as a flash crowd. It's a sudden, unanticipated growth in demand for a particular object on the internet. Imagine a highly anticipated movie trailer dropping, or the final match of a major sporting event. If all those millions of users try to connect to a single traditional server, well, there simply isn't enough bandwidth. The server gets instantly crushed and the whole site crashes. Game over. So to survive a flash crowd, we have to zoom out. Section 4, the global solution, content delivery networks, or CDNs.
Back in the late 90s, the internet was growing so incredibly fast that popular sites were constantly crashing. People actually mockingly called it the World Wide Wait. To solve this, companies like Akamai pioneered the CDN distribution tree. Instead of one single origin server trying to talk to millions of clients, it acts as the top of a tree, replicating its video files out to CDN nodes located in regional data centers, places like Sydney, Boston, and Amsterdam. When users worldwide want the video, they don't even talk to the origin server. They just fetch the files from their nearest regional node. But how does your computer automatically know which node is closest? The really clever bit here is DNS redirection. When you click a video link, a specialized CDN DNS server intercepts your request. It looks at your IP address, checks the current network distances, and evaluates the load capacity of all its servers. Then, it seamlessly returns the IP address of the absolute closest, fastest, most lightly loaded server. So Amsterdam clients get routed to Amsterdam, and Sydney's clients get routed to Sydney, entirely behind the scenes without you ever having to lift a finger. By utilizing these massive server clusters to handle immense traffic, the entire CDN setup basically becomes the ultimate win-win-win scenario. First, the user gets incredibly fast, responsive video. Second, the content creator actually survives those massive flash crowds because the CDN absorbs all the heavy lifting. And third, your local internet service provider saves a huge amount of money because the video data is served locally rather than clogging up expensive, long-distance network bandwidth. It's really quite brilliant.
And that brings us to our final section, the future of the global tree.
We've taken an incredible journey today, from the extreme micro level of RTP packets and parity math, all the way out to the macro geography of global content delivery networks, which leaves us with a final, somewhat provocative thought. With video traffic growing exponentially every single year, and higher resolutions like 4K and 8K becoming the standard, is there a limit to how much our global networks can handle? It's a fascinating puzzle to ponder the next time you hit play. I really hope this explainer has completely transformed how you look at streaming media. Thanks so much for learning with me today, and keep exploring.